Welcome everyone, and thanks for joining us today. I'm Darren Brown from Arkeso Lightweight on behalf of the Expanded Shale Clay and Slate Institute. And today's presentation is on how lightweight block enhances every CMU wall property. And Kevin Cavanaugh is our featured speaker. Just a little bit about ESCSI. We are the International Trade Association for manufacturers of rotary kiln produced expanded shale clay and slate lightweight aggregate. ESCSI promotes the extensive use of rotary kiln-produced lightweight aggregate in the lightweight concrete masonry, structural lightweight concrete markets, as well as use in asphalt, geotechnical, green roof, horticulture, and water treatment applications. Today's speaker, as I said, is Kevin Cavanaugh. He currently chairs ACI TMS Joint Committee 122 on the energy efficiency of concrete masonry systems, that is charged with developing national energy code standards, as well as chair of NCMA's Masonry Communications Subcommittee. He has worked for large multinational and small family-owned CMU manufacturing companies. He enjoys the people in the concrete masonry industries and educating owners and architects on masonry's many benefits. Just a few housekeeping notes for the attendees before we begin. Please mute your audio and turn off your cameras to help with bandwidth. If you have any questions during the presentation, please type them in the chat box and we'll can answer them there. And with that, we'd like to welcome Kevin Cavanaugh to present how lightweight block enhances every CMU wall property. Kevin?
Thank you, Darren. Well, good morning, everybody. Again, my name is Kevin Cavanaugh. I'm coming from you here in Milwaukee, where we have a typical sort of gray spring day. I'm going to turn my camera off in a minute or two. I want to make sure that the bandwidth here doesn't get messed up with, I have dueling webinars in another room in the house. So this is a AIA registered or will be registered presentation, a little bit more bookkeeping. For those of you that need the learning objectives for AIA, we're going to learn what smart wall CMU are, understand how they outperform normal weight CMU, develop awareness of that lightweight next gen CMU greatly enhanced wall performance, and then learn how to properly specify these materials. If you need a certificate of completion, I think everyone indicated when you registered, if you want one, we'll be sending you a certificate like this. For the AIA folks, we can register you as well. If you have any questions, Darren and Abigail will be monitoring the chat box, so type them in there. At the end of the presentation, we should have a little bit of time available to take, verbal questions, so you can save them until that point in time if you want. Darren mentioned briefly the products that were used in today. Expanded shale clays and slates have a long history dating back to 2,000 years ago, the Pantheon in Rome. It was a natural lightweight aggregate from volcanic activity. It's used in the dome. It still performs today. Modern lightweight aggregate was one of those, if you're given lemons, make lemonade. It was a Kansas City clay brick manufacturer named Stephen Hayde. He recognized or realized some of his product, as you can see there, highlighted, were coming out of the kiln with these little blobs of different type of clay material. And that was the beginnings. He looked into this a little bit more closely and realized that that was essentially a new product that he was making there, expanded shale clay and slate. He patented that in, I'll turn my camera off. He patented that in 1918, so about 100 years ago. And he promptly actually gave the patent to the US government for World War I to make ships. The Navy, we had a shortage of steel. Some of those ships are still used as research labs, Galveston Bay, River in British Columbia. Take samples from those, and the concrete is performing incredibly well, incredibly structurally efficient material, continues to gain strength after almost 100 years. The way we make lightweight aggregate today is in a rotary kiln, so it's not it's sort of a controlled volcano, if you will. We heat the material at temperatures approaching 2,000 degrees Fahrenheit. It is not as hot as a cement kiln, which gets upwards of 2,800 degrees. The raw material that is quarried, or depending on the source, if it's clay, shales, or slates, sometimes you have to dig it up, quarry it. Sometimes you can scoop it out if it's clay, essentially with excavators. The material goes into the kiln, it's heated up, it expands. It's not a drastic, rapid expansion like popcorn, and it doesn't melt completely like cement manufacturing does. When the material leaves, that's a shot of the inside of the kiln. I think you can see my cursor. It's sort of rolling as the kiln spins, and the kiln is tilted, and it leaves the kiln. It's cooled off. You can see these particles here are basically crushed in half. There's a coating on the exterior, and there's a lot of pores. These pores are not interconnected by and large. If you look at a closer shot, you can see it almost looks glassy and ceramic-like. So this is what we like to call modern day expanded shell clay and slate material. And most people recognize it this way, simply in that the same mass, in this case I think it's a pound, basically the volume of the lightweight aggregate occupies at least twice the space, so you get more material per pound. But there are a lot of other benefits that this product has other than weight, and we're going to touch on some of them and some of the other applications, but we're going to focus on lightweight block, and then I'm going to do a ComCheck example with the energy codes and masonry. There are 16 plants in the US, as you can see the yellow dots there. It's spread around fairly geographically across the country, you know, good distribution. However, you can maybe recognize there are some blank spots, but we do a lot of efforts in the industry with transportation. A lot of what we do is, you know, we barge, we rail, and obviously we truck it. But we're able to fill almost every spot in the country. In fact, I would say we do efficiently with the red dots. You can see there, those are distribution yards, be a combination of docks along rivers, rail spurs and terminals. So we were able to effectively cover the whole entire US 48 states, no problem. Some of our members actually will export material overseas and into the Caribbean. Darren touched lightly on where the material is used today. You can see steel frame metal deck building there. You can see a double T for a parking garage. On the right-hand side, lightweight geotechnical fill, green roofs and rooftop gardens, and essentially just planting media for horticultural works incredibly well. This material imparts good benefits to the soil. In fact, there's some efforts in the cannabis industry where they've looked at using lightweight aggregate chip seal on the bottom right, bridge decks. In fact, I grew up in the Washington, D.C. area, and just about every bridge over the Potomac River there has a lightweight concrete deck, or it's been replaced and repaired with a lightweight concrete deck. We're going to focus today, as I mentioned, on, or as Darren mentioned, high performance concrete masonry, and specifically with smart wall, and that's a term that the ESCSI coined to sort of generically talk about lightweight block. But smart wall helps CMU they're obviously lighter, they're going to be stronger. The specification that we recommend going to provide higher R values, better fire ratings, lower wall costs. It's a lot easier for the mason to pick them up and lay them, obviously. They're lighter. You can get more block per truck. I'll show you an example of that. And they also have lower silica content. So we like to think lightweight block enhances every CMU wall property. Just a quick diversion here for fire safety. Lightweight block are easier to get fire rated block. When you make them out of lightweight aggregate, you don't have to use as much material. But in general, everyone is probably familiar with the fact that we now have the International Building Code, which was a combination of the three model codes from 15, 20 years ago, the Southern Building Code, Uniform, and then the BOCA. But Project Failsafe, a bunch of fire marshals looked at this and they've realized over time that the actual fire safety scores have dropped as a result of this. We have a whole presentation on that. I'm not going to go into it today, but you may recognize fires like this are happening all over the country where you have a pedestal. It's either poured concrete or concrete block, and then on the top, 3 or 4 stories, you have a very well-organized lumber yard. Oftentimes, these things catch fire. There are no active systems involved. Usually, the whole thing burns down. The only thing left remaining is the non-combustible concrete or masonry. We dig up a lot of data from NFPA. There are cost studies that have been done to show how cost-effective masonry walls are versus other systems. And even most recently, everyone's probably aware that the cost of lumber is skyrocketing, whereas masonry is pretty much consistent or constant. So that's another presentation we have. So here's a typical 8-inch block. The ASTM specification for that is ASTM C90. The strength is 2,000 PSI, that's the minimum. There was a change about 10 years ago now that used to be, I'm sorry, I'm confusing a different ASTM, but there was a change about 5 years ago where the minimum strength is now 2,000 PSI. It used to be 1,900. And the density categories for heavyweight, normal weight block are made with concrete that weighs 125 pounds a cubic foot or more, medium weight 105 to 125, and lightweight less than 105. So in an 8-inch block, as you see here on the bottom right, that's going to lead to, with 3 webs like that, typically about 28 pounds. That's how much the block will weigh. Smart wall units, they are made with high quality structural grade lightweight aggregate, expanded shell clays and slates, and that aggregate meets ASTM C331. There is a specification for natural stones and gravels, ASTM C33. This is just the lightweight version of that, 331. So they meet C90, but they exceed it. Smart wall units do in 2 important ways. They're going to be stronger. 2,500 PSI is the minimum strength, and that's going to give you 25% stronger block versus typical ASTM C90. And they're going to be much lighter. They're going to be less than 93 pounds per cubic foot. The 93, you might wonder why that's not a round number. That goes back to when there was a big effort to have the SI or the metric system imparted throughout the country, and that translated to 1,500 kilograms per meter cube. I do know that there are producers of smart wall units or lightweight units that actually go down to 78 pound per cubic foot concrete. So in a typical block, an 8-inch block, you're going to have a 40% lighter unit in an 8-inch unit. And you can make them so incredibly light, in fact, that even this young lady can pick them up and not struggle with them. So here's some comparisons. A typical 8 by 8 by 16, 25 pounds versus 40 if it's normal weight. 12 by 8 by 16, 35 pounds versus 53. And in many places, once you get above a certain weight, the unions require you that you have a 2-man to pick up that block. So both of these normal weight units in some markets would exceed the 1-man limit or the 1-person limit. So again, it's going to be lighter and it's going to be stronger. I have some duplicates there. So the lighter part is very crucial for keeping wall costs competitive, or in fact lowering them. When you look at what's involved or the costs that are in a finished masonry wall or CMU wall, it's the cost of the block to make, the freight to deliver it, the labor, and then life cycle energy costs. And I'm gonna focus on an example with the energy code towards the end of the presentation that shows how lightweight block make it easier to do this, to meet the energy code. So the economics of lightweight masonry, many markets around the country, you'll hear masons will say lightweight units cost more. You know, if I was to superimpose on the map of the lightweight aggregate plants, quarries and natural stone, you know, it would probably be 20 times as many dots. lots more locations of normal aggregate. So there's sort of a thought that, oh, lightweight aggregate costs more, the units cost more. But the point is, when you install it, about 60% of the wall, and in some cases even more, is the mason's labor to put it in the wall. So when we operate on that 60%, and the cost of the block usually is not really a big factor, but you know, the way the industry works, everyone knows low bids tend to win, and a mason contractor thinks that way when he looks at pricing his block. So we have an education effort that's been ongoing for quite a while. It started with some studies done in the late 80s. It's a combination of the Expanded Shale Clay and Slate Institute, NCMA, National Concrete Masonry Association, and the Mason Contractors Association of America. And it was a demo project at a warehouse in St. Louis. First, they looked at the effective weight going from normal weight units, 16-inch normal weight, to a 16-inch lightweight, or a 24-inch long normal weight unit to a 24-inch lightweight one. And the increase in productivity just going to lightweight material was about 15 to 19%. If you looked at a 24-inch long unit, there are some markets today that are making even longer units. They're starting to be installed, believe it or not, by a miniature crane to assist the mason, but there are some places where the manpower will still do it. But if you look at the size difference, going to a 24-inch in length unit, you get a 40% increase roughly for both 8s and 12s. And when I say 8s and 12s, that's the depth or the width of the block. If you combine those two, you're going to get an increase in productivity of about 65%. So that catches a lot of people's attention. A lot of mason contractors like to dwell on that, especially the masons down in the Louisville, Kentucky area. I know there's a producer down there, a block producer that makes very lightweight units. The masons love it. They're very successful. Up in the Chicago area, closer to where I live, a producer made 24-inch long block on a project about 10, 15 years ago. And it was 50% larger units. It was, sorry about that, 3 pounds lighter than a typical 8-inch. Productivity was, you know, this is what they had to do to break even in the red. The lightweight that they actually did install was 250 units a day. I think somebody needs to be muted there. I'm not sure what that is. The increase in productivity needed on this particular job was double what was needed to offset the price and premium. And man days wise, they actually reduced the length of time to complete the project. So that's always a good thing. 17.5 fewer days, reduction of 23%. There are some charts that have been around, estimating books, for a long time. If you look at this chart, the heavier units are towards the top left there. So if you have a unit that's 107 pounds, they figure you'll get 53 in a day as you come to the bottom right. Let's look at a 24-pound unit in this area right here. You can lay 168 of them. So that's borne out by that project in Chicago, as well as the study that was done years ago in St. Louis. One way to use this chart or to look at this chart is if you consider a mason's wage, and these numbers are a little bit old, they're dated from Southeast US. I think it might have been the Florida or Georgia market. Normal weight block weighing 37 pounds, lightweight 28, smart wall 24, you would lay 137 or up to 168 block a day. If that building they were building, let's say it was a Walgreens or maybe a small Target, had 60,000 block, it would take normal weight block where you lay 137 a day, 438 days to complete that. Or if it was the smart wall units, the light ones, 357. So that's a lot of savings that accrues to the mason contractor and to the owner. And I didn't mention, but you can see on the chart here, there's this line where it says a 2-man block, 37 pounds. Another way to look at it is there are some estimators or mason contractors that think or figure that a man or mason can only lift so much weight per day, or I don't know whether this is an old union rule or not, 6,000 pounds. So if that's the limit that you can lift a day, I know like today, UPS, FedEx, they have, if it's over 75 pounds, you have to do something special to ship it. So normal weight, 37 pounds to smart wall, you could lay 162 or up to 250 if it was the smart wall. Again, so depending on how you look at it, the savings here are quite a bit more. So what that savings of 39 cents means is that the premium for that block would be 39 cents, and the mason contractor would break even. The owner of the project would get the job in 130 days sooner, which is quite a big change. One thing I do want to point out quickly, since we're talking about mason contractors, is that expanded shale, clay, and slate material has lower silica content than natural sand and gravel. So that's a good thing, considering that there is a lot of cutting that goes on masonry sites, and there are special types of saws, but it's real good to know that you have a product, an aggregate that reduces the amount of silica. It might be a little hard to see this on your screen. It's a little small on mine, but the crystalline silica volume in expanded shale clays and slates is very low. It's 1/3 of granite, 1/8 of natural sand. So when you look at what this means over a typical workday, in your cutting block, the crystalline silica exposure is below the action limit that OSHA sets, which is a great thing. I'm not recommending that masons wouldn't take protective measures, but it's just nice to know that if this particular product here, aggregate, you don't have to worry about it really. So let's focus now on structural efficiency. We're going to have a better strength to weight ratio here with smart wall units. The industry for many years was very conservative in the way we approached. This would be the concrete masonry units testing and our tables for what the strength of the wall would be, or what we call F'(M). That is not the strength of the block, that is the strength of the wall itself. That's what the structural engineer uses. In ready-mix concrete, we're familiar, it's F'(C). But there were changes made to the design code in 2014 that recognized that modern production, modern installation, we were getting way more strength in the wall than the table that had been there for a long time. Another change, and I'll get into more detail on that table in just a second. There was another change 10 years ago in ASTM C90 that resulted in what we generically call next generation block, or CMU. I use those terms interchangeably, where you can now have up to 5 times less cross-web area and you get the same structural performance. Both of these, the change in the design strength from 2014 and ASTM C90 in 2011, have big impacts on units that are being produced and installed in the market today. First, I want to show you the old table, the TMS table here on the left. 1900 PSI used to be the minimum strength that you could have to meet C90, and that translated to, if you built a prism, or if most cases they wouldn't build prisms on a job site, which is 2 units laid together with a mortar joint that you then take to a lab and break it. Rather than do that, a lot of people just use this table, and a 1900 PSI block with type MRS mortar would give you the equivalent of 1500 PSI in the wall. If you wanted to get to 2500 PSI, you had to have a 3750 PSI block, an even stronger block with a slightly weaker type N mortars. So this table was used for a long time. The industry looked at this and realized, well, our block, modern production, et cetera, they did some correlation testing that sailed through TMS fairly quickly. Today, the minimum is 2000 PSI strength, which gives you 2000 PSI in the wall, and 2500 also gives you 2500 PSI F'(M). So that results in quite a bit of strength increase in the wall that the structural engineer can use. When you have this increase in strength, you can reduce the amount of rebar that you have in the wall, or you can make the units thinner. Instead of a 12-inch wall to go 24 feet tall, you could go with an 8-inch unit and save material costs there. Some of the other practical effects, like I mentioned, less reinforcing, which then allows you to have more insulation, which is going to make it easier to meet the code, the energy code. You could have possibly less route for dead loads, not deal loads. There's a typo there. And you're going to have less seismic force if you are subject to a seismic event, because the mass of the walls is lower. Everybody, well, I'll just move on. I was going to quote Einstein, F equals ma. So here's an example wall of what's happened as a result of the changes in TMS. I know it's a little hard to see the table, but it's an 18-foot wall, 8-inch CMU, 40 PSF wind pressure, 3,000 pounds per foot axial load. And if you look at the 2009 to 2012 to 2015 IBC, the rebar requirements were that you had to be 40 inches on center vertically, which now you can space them as far apart as 96 inches, which is a lot less steel being used, which means you have a lot more insulation in the wall, which means you're going to have higher R values. So 40 to 48 to 96, which leads up to ComTech example that I'm going to get to shortly. And there are presentations, and I will reference Nick Lang from NCMA. He gave a presentation a year or two ago to a block producer in Iowa, and I was able to share it in Michigan 2 years ago over in with a producer in Iowa. So what we want to look at is the ComTech example that I mentioned. You get higher R values with a block, make it easier to meet the code. If you're not familiar with ComTech, you get a printout that looks like this. I'm going to cover this in detail here in a minute. At the bottom, you can see where it says an envelope passes a design is 0% better than code. This is an example where we just took the prescriptive requirement and plugged it in for the walls. And I know it's hard to read that probably on your screen, but I do want to take a little, since we have some time, a little mention of some of the reference documents. AIA always likes for the speakers to provide a little bit of background on where their information is coming from. So here's one of them. This is an NCMA article that appeared in a magazine about the time the ASTM C90 change in 2011 happened. Basically, smaller webs equals higher R values. It's written by Jason Thompson from NCMA. He's the VP of engineering. This mason here laying these units, that's a one web unit. It's probably a jail or some type of heavy industrial facility, because you see the bars are heavy seismic zone. They look like they're placed every 8 inches. But generically, one way to think about next generation block, you're going to have skinnier webs. And if you look there visually on the right-hand side, skinnier webs means you have more space available for insulation and you get higher R values. If you look on the left here, this is an old pear-shaped, as we called it, or a tapered web. So the webs can be thinner. You're going to have better thermal efficiency as a result. You can make them in 2 web units, as you see here on the left, or one web unit, as you saw, as you see on the right in that earlier photo. In the industry, sometimes we call these A block or H block. On the outside, the block is still going to look exactly the same. You're going to get the same performance structurally. The dead loads are all carried by the face shells. When we lay the block, we always use face shell bedding only. We don't typically put mortar on the cross web. So the load bearing surface area has not changed. So just graphically, and you can see here, this is a combination of A block and H block. You have a lot more insulation in that wall. NCMA has a thermal catalog on this. It has values in there, and the reason these catalogs are important is to use ComCheck. You need to put customized values of the U value and the heat capacity of the unit, which is a proxy for thermal mass performance. You have to put customized values into ComCheck because ComCheck has embedded values that are very, very conservative, and they're based on insulation types, loose fill insulation, vermiculite and perlite, that are almost never used these days. So you can see this catalog that NCMA has, there's three web, two web, one web units. The Expanded Shale Clay and Slate Institute has a version of this that they've been working on. There are individual manufacturers that have this. It makes it easier to meet the code. One other thing I need to point out is I'll skip ahead, there are units coming into the market. You can see this is a two web unit. This is locally here in Wisconsin, where if you look on the bottom right now, you can see that grouted cell has an insert, and we also then foam the ungrouted cells. This is a different version of a hybrid unit with two webs, where this would be the grouted cell here. And the reason I referenced this paper, Dr. Bennett from the University of Tennessee, is he did some research to make sure, and I'm not going to go through this in detail, but you can see the drawing here. Here's a typical block. There's the grouted area. There's the installation insert to let us know, and I know you were not able to read that, but you can use these units and you're not going to have any degradation in your structural performance. Or it's a minimal degradation, I should say. It doesn't have a big effect, and you can design around it. So very quickly, I use that term next generation block. What you can make, and will still meet C90, is units that have as little as 4.5% web area. All these examples here are next generation units. What's being commercialized are two web units, like the one in the bottom middle. Here's a typical old-fashioned 8-inch block. You can get as low as 4.5%. An old block had 21% cross web area, and the cross web area is simply the three webs. They're 7 5/8 tall by 1 1/4 inches. You multiply that out and you divide it by the 8 by 16 face of the block. So it's a reduction, can be up to five times less. We're not seeing too many units like this. What you tend to see is a two web unit like that. So the benefits of next generation block: faster install, higher R value. Sounds just like the benefits of lightweight block. Sounds like the benefits of smart wall, and indeed they are. When you combine all these things, you get concrete masonry units on steroids, perform very well. Mason can complete more jobs, fewer injuries, healthier masons, more profits. Easier to meet the code. They're green. There's less material in them. Two web block, like I showed on the prior screen. Sorry about that. The two web block would have about 10% less material than a typical 8, or 25% less if it was a 12-inch unit. So less material means fewer delivery trucks to bring the aggregate to the block plant, less energy to cure it in the kiln, accrues to beneficial sustainability terms. The next gen block combined with lightweight block, there was a study done in North Carolina. These A blocks are much easier to maneuver, and the productivity they found on the newer study in North Carolina was quite a bit above what reference documents would say, 100% above what NCMA's tech note had. A lot of that has to do with this rebar and this open end. You do not have to lift the block up and over or struggle like that mason in that photo earlier, even though that was the rebar 8 inches on center. And you can use less rebar because you don't have to have any lap splices potentially. You can just put the length of the bar into the footer and build your wall 12, 18 feet, whatever it is, and you wouldn't have to have any lap splices. So that's a benefit as well. So when you make these units with lightweight aggregate, and this is the insulating foam here that's typically used today, you're going to get 2 to 3 times higher R values. These are numbers right out of Jason Thompson's thinner webs equal higher R value article I showed you earlier. 8-inch old-fashioned block filled with foam would give you an R value about 6. Next generation version of it gives you an R value about 15. Same sort of trend with 12-inch block. I'm going to stop there for just a moment. Do we have any questions, Abigail or Darren, so I can take a quick sip of water?
No, not yet. You're doing good, Kevin.
Thank you. Okay, just wanted to check. So we're going to get into a little more detail with this concheck example. It is a warehouse. There's a little loading dock, 2 overhead doors. There's probably a little space up front where it's office. If you look at and I know that table, you can't read it. That is the prescriptive R value table out of the energy code. What is in that table, and this is easier to read, are requirements for each of the 8 climate zones that make up the continental US. Well, I guess Alaska's in climate zone 8, Hawaii's probably 1 and 2. But there are minimum R values for roofs, walls above and below grade floors, slabs, etc. And then different types of roofs, different types of walls, floors, and so on. And that's why that table has so many numbers in it. And I took the R values out of that table and retyped them here. It's a little easier to see. And each of the climate zones are represented here. I'm in climate zone 5 and 6. And if it was a residential wood frame wall in Wisconsin, I'd have to have an R value of 20 between the wood studs plus 5 continuous is what this means. Or if it's a commercial building, not a residential, this could be an apartment building, I would have to have R13 between the studs and 7.5 CI, continuous insulation. Well, a lot of the competitive wall systems will show designers this table. Well, they'll show them this table that's in the code, and they'll explain that because you have this plus 10 or this plus 7.5, that means you have to have continuous insulation, and continuous insulation is like sheathing on the exterior or drywall on the inside. If you're going to do that in a masonry wall, you're going to have to do it in a cavity wall, which increases costs and doesn't allow you to do single white walls. So I'm going to just show you, here's an example I'm going to do a mass wall in our climate and comm check. But the one thing I need to say, and everyone needs to understand, if you use this table, this is the only time continuous insulation is mandatory. There are 3 other ways that you can meet the code where continuous insulation is not mandatory, but the competitive wall systems, they don't share that information with you. So I'm going to share it with you now. And the definition, here's ASHRAE's definition. That's ASHRAE's the folks who write the standard 90.1, which gets adopted as the IECC by the International Building Code. Continuous insulation is continuous across all structural members without thermal bridges other than fasteners and service openings. So you have to be able to adhere this continuous insulation somehow, anchors or nails, screws, etc. But it is not mandatory. There's 3 other ways to meet the code. There's this, the first one is what they call the prescriptive U factor, and U factors are simply the inverse of the R value. So this 0.09 down here, if you take the reciprocal of that or the inverse, that's going to give you that R11 that I showed you earlier. But in this table, you do not have to have continuous insulation. The U factor is the average of the overall wall. It usually includes the walls, windows, etc. So here's the floor plan of this warehouse. And we're going to look at 3 different block types, maybe 4 different block types. Option 1 is a 12-inch block, medium weight. Option 2 is an 8-inch block. And then option 3 is next gen with inserts. So in this comm check run, if we plug in the minimum R value from either the prescriptive R value table, or you can see here where my cursor is, the U value of 0.091, I'm sure that's small on your side. And we have the area for the walls, the windows, the doors, etc. So the areas are all here, the R values are here, this is the roof. It passes the code and it's 0% better. The green line means we're good, we pass, we comm check, but we're not any better than the minimum, which makes sense because we plugged in the exact U value requirement. So if we were to try to build this with a medium weight unit, 115 pound per cubic foot, foamed in place insulation, vertically grouted 120 inches on center. I guess there's some extra steel in this example. This comes from NCMA because of the bond beam at the roof. It's about 86 inches on center. If we look at a typical 12-inch block, we can go to a manufacturer, we can go to NCMA's website and plug in the geometry of this unit and fill it with foam, and we'll find out that we only have an R value of 7.19, which is a U factor of 0.139. What we need is up here. We need the 0.9 or the 11.1. We're not going to be able to build this building with this type of block and pass the energy code. So let's look at a different example. Let's look at an open-ended next generation block. Plug it into NCMA's calculator or get the value from the manufacturer, and we're still a little bit short. It's an R value of 10.14. We're not going to get there. So let's, I think this slide got out of order. Oh, I'm sorry, it's not out of order. We plug it in, but what we had to do in order to pass, this is the yellow highlights or the U factor of that unit, but up here at the very top, I should have just highlighted that right there. The roof insulation changed from R30 to R38.5, and we're able to pass slightly better than code. So you can, we might have been able to do that with the other unit as well, but the R value of the roof had to go up quite a bit more. So let's see if we can get this to pass using lightweight. So we're going to now use a lightweight unit. The R value is 11.23. This is the C90 lightweight, so it's 105 pounds. It's not as light as the smart wall I've been talking about. And we put the insulation in the roof back to 30 where it was originally. We plugged in the new 0.089, and we're 1% better than the code. Let's see if we can do it with an 8-inch unit. 8-inch with medium weight, the R value is only 4.73, U value 0.211. We're not going to get there, but we could try to use an open-end unit. We still don't get quite where we need to be. The R value is still about half of what the minimum code required. So we'd have to put a lot of insulation in the roof, or we could finish out, fur out, and put finishes on the inside of the building. This comes out of NCMA's catalog. This looks like, it's a little hard to read, but there's polyurethane insulation in the block, and there's some insulation that should be between the studs. You don't have to finish all the interior surfaces when you use ComCheck. We could just do 3 walls of that building, bump the R value or lower the U factor on 3 of them. It's a little hard to see this, but this was originally where we started, 0.151 with just the block, and then those furred out units, we get a much lower U factor. The roof is back where it was, and we're able to pass the code. But there are many, many examples where they want to have a hard surface on the interior, or they don't want to fur out the interior at all, and that's what leads us back to using lightweight all the time, or next generation lightweight or hybrid units, and I'll show you that here shortly. So I mentioned you didn't have to finish off all the walls, and you wouldn't have to finish off the entire elevation of any given wall. This is the flexibility that ComCheck gives you. So now the north wall, we broke it into 2 different types of units or finishes. This is where you have the furring and the insulation. This is just the block where my cursor is 0.151. We're 2% better than the code, which is a little bit better than where we were. There are also next generation unit like this I showed you. They have inserts. These tend to be more expensive than just foaming a block and whatever generic block you have, but NCMA's calculator will handle very simple units that have 1 insert over the face shell. And you can see when they plug that in, you get up to 8% better than the code. But these types of units, you always want to verify and get test data from them, hotbox test data, because there are some folks that tend to over-exaggerate. They confuse thermal mass performance, and they add that into their steady state R value, and that's not what the code allows you to do. So, we're able to get single white walls. This is in Alaska, University of Alaska at Fairbanks. You can see in the winter -43, summertime 93, Walgreens and AutoZone, we're able to get those buildings to pass the code. Oftentimes, lightweight units are going to make it easier, and then smart wall units that are even lighter make it a step further. And then if you're in the Louisville, Kentucky area, they have really lightweight units, and it's a piece of cake for them. But in summary, as I get ready to conclude and leave some time for questions, smart wall block, they're lighter, stronger, going to give you higher R values, better fire rating, lower wall cost, and lower silica content for masons installing them. The learning objectives we covered, you learned what smart wall are, understand that they outperform normal block in many ways. Lightweight, next generation, the third one, even take it a step further. And then finally, I haven't covered it yet, but I will show you here in a second. The way to specify this is pretty straightforward. 93 pound per cubic foot maximum density for the concrete. They have to be 2,500 PSI strength minimum, and the material has to be expanded shale, clay, and slate. We have a sample guide spec, but it's really those three items right there that will get you the smart wall unit across the country. And you have to remember, it's really only one cost. It's only one takeaway. It's not the cost of the block; it's the cost of the wall. But really, you should also consider there are two takeaways. You're going to have a better product. You're going to have, like I just mentioned, better energy, fire ratings, seismic, structural, so on. So that's our little how lightweight block enhances every CMU wall property presentation. And Darren or Abigail, if you've had anybody type in questions, be happy to we can cover those, or if someone wants to raise your hand, we could open up the mic to them possibly. I'll put the control back in your hands, Abigail. I'll turn my camera back on. Thank you, everybody.
Thank you, Kevin. If there's any questions, if you can feel free to type them in the chat box, or if you want to just go ahead and turn on your mic and ask away, Kevin would be more than happy to answer those at this time.
Are they able to turn their mics on, or does Abigail have to give them that ability?
I think she can give him that ability.
Yeah. I can do it, or they can do it on their own.
Okay. So far, nothing's come in.
Well, while people are thinking or typing, I'm really glad that I was able to present today. I appreciate the opportunity. I look forward to being able to do this in person shortly. I know one of our trade association affiliates, National Concrete Masonry, they have plans to have their summer meeting here in Milwaukee. It's gorgeous here in Milwaukee in the summer. Please come up. You can obviously drink some beer here, get some good cheese, have fun at Summerfest down on the lakefront.
Okay. Well, I'm not seeing anything and come up. So, well, Kevin, once again, thank you and for the great presentation, and appreciate all the attendees for joining us today. We'll be sending out a survey following this webinar, and would appreciate any feedback that you have. Certificates for CEHs will be sent out to those who requested those. And we hope you'll join us for any future webinars posted on our website at escsi.org. So thank you again, and hope everybody enjoys the rest of your day.